Hello and welcome to this 15th set of problems on complex numbers. In this set, we will solve problem number 141 to 50. And as I always say that should pause the video when I'm stating the problem. And only if you cannot solve the problem, you should look at the solution. So without further ado, let's get started. Problem 141 says that the complex numbers Z1 and Z2 are such that R is missing. Z1 is not equal to Z2 and mod of Z1 is equal to mod of Z2. If Z1 has positive real part and Z2 has negative imaginary part, prove that Z1 plus Z2 by Z1 minus Z2 is purely imaginary. So we are given that mod of Z1 is equal to mod of Z2 and real of Z1 is greater than 0 and imaginary of Z2, this should be Z2 is less than 0. So from the formula we know that real part of any complex number is equal to half of that complex number plus complex conjugate of that number. So we have half the complex number Z1 plus Z2 by Z1 minus Z2 and plus complex conjugate of that is mod of Z1 plus bar of Z1 plus Z2 bar divided by Z1 bar minus Z2 bar. So if we solve this by multiplying the two denominators and then multiplying the corresponding numerator with the other denominator, then we get this as 1 by 2 into mod of Z1 square minus mod of Z2 square divided by mod of Z1 minus Z2 whole square. Now since mod of Z1 is equal to mod of Z2, the numerator would be 0, making the whole thing 0. So that means the real part of this complex number, that is Z1 plus Z2 by Z1 minus Z2, is 0, making it purely imaginary. Problem 142 says that if A Z1, B Z2, this should be Z2, and C Z3 are the vertices of a triangle ABC in which angle ABC is equal to pi by 4 and AB by BC is equal to square root of 2, then prove that the value of Z2 is equal to Z3 plus I Z1 minus Z3. So we are given that AB by BC is equal to square root of 2. We are also given that angle ABC is equal to pi by 4. Thus, for that angle, we can say that Z1 minus Z2 by Z3 minus Z2 is equal to mod of Z1 minus Z2 by mod of Z3 minus Z2 into e to the power I pi by 4. Now this mod of Z1 minus Z2 is nothing but AB. Mod of Z3 minus Z2 is nothing but BC. So we substitute that and put the value of square root of 2 and we expand for e to the power I pi by 4, which would be cos pi by 4 plus I sin pi by 4, which we have written as 1 by root 2 plus I by root 2. Now we multiply this root 2, which will cancel out the denominator root 2, giving us a complex number 1 plus I. So we see that Z1 minus Z2 by Z3 minus Z2 is equal to 1 plus I. So we cross multiply, we get Z1 minus Z2 is equal to 1 plus I into Z3 minus Z2. We bring out all the terms of Z2 on one side and solve, we get Z2 is equal to Z3 plus I into Z1 minus Z3. Problem 143 says that if Z1 and Z2 belong to complex number set, Z1 square plus Z2 square belong to real numbers, and we are given two equations, Z1 into Z1 square minus 3Z2 square is equal to 2 and Z2 into 3Z1 square minus Z2 square is equal to 11, then we have to find the value of Z1 square plus Z2 square. So we have two equations. We multiply I to the second equation and add it to the first equation. We obtain Z1 cube minus 3Z1 Z2 square plus I Z2, 3Z1 square minus Z2 square is equal to 2 plus 11I. Now the left hand side is nothing but Z1 plus I Z2 whole cube is equal to 2 plus 11I. Similarly, we multiply the second equation with I again, and this time we subtract. We get left hand side as Z1 minus I Z2 whole cube is equal to 2 minus 11I. Once we have these two equations, we multiply them. Multiplying these will give us Z1 square plus Z2 square whole cube is equal to 4 plus 125, which is equal to 125. Cube root of 125 is 5. So Z1 square plus Z2 square from here is equal to 5. Problem 144 says that if square root of 1 minus c square is equal to nc minus 1 and z is equal to e to power I theta, then find the value of c by 2n into 1 plus nz into 1 plus nz, 1 by nz. So we are given that square root of 1 minus c square is equal to nc minus 1. So we square both sides, we get 1 minus c square is equal to n square c square minus 2nc plus 1. So 1 will get cancelled. After that, 1 power of c will get cancelled. So we will have c by 2n is equal to 1 by 1 plus n square. Now what we have to find is c by 2n into 1 plus nz plus 1 plus n by z. So we substitute the value of c by 2n, that is 1 plus n square, and we multiply the other two terms. We get 1 plus n square plus n into z plus 1 by z. Now z is e to the power I theta. So e to the power I theta plus 1 by e to the power I theta, which will be e to the power minus I theta when brought to numerator, will give us 2 cos theta. Now this is not plus n. This should not be plus n. This should be multiplied with 2 cos theta. So then you multiply this, expand this, 1 plus n square will get cancelled with 1 plus n square. We will have 1 here, and this 2n cos theta divided by 1 plus n square will come. So now 2n by 1 plus n square is equal to c from here. So then the whole result is 1 plus c cos theta. Problem 145 says that consider an ellipse having its foci at a z1, b z2 in the Argand plane. If the eccentricity of the ellipse is e, and it is known that that origin is an interior point of the ellipse, then prove that e belongs to the set of 0 to mod of z1 minus z2 by mod of z1 plus mod of z2. So we take any point pz on ellipse, then the equation will be given by mod of z minus z1 plus mod of z minus z2 is equal to mod of z1 minus z2 by e. Now if you substitute z1 or z2 in the above equation, then left hand side will become mod of z1 minus z2. So for any interior point on the ellipse, we can say that mod of z minus z1 plus mod of z minus z2 is less than mod of z1 minus z2 by e. Now since p lies on the ellipse, we have the original equation here. Now it is given that origin is an internal point, so 0 minus z1 plus 0 minus z2 is less than mod of z1 minus z2. Sorry, I misread that. Mod of minus z1 plus mod of minus z2 less than z1 minus z2 mod. So thus we see that E will be lying in the set of 0 to mod of z1 minus z2 by mod of z1 plus mod of z2. Problem 146 says that if z minus 2 minus I is equal to mod of z into mod of sine pi by 4 minus argument of z, then find the locus of z. So we take z is equal to x plus iy. So we will have on left hand side mod of x minus 2 plus iy minus 1. On right hand side would be mod of z into 1 by square root of 2 cos theta, because sine of argument of z would be tan inverse theta. So sine tan inverse theta would be cos theta. Sine pi by 4. So cos tan inverse theta would be cos theta. And then we have minus 1 by root 2 sine theta, where theta is argument of z, that is tan inverse theta. Not tan inverse theta, tan inverse y by x. Argument is theta, not tan theta. So now left hand side will be square root of x minus 2 whole square plus y minus 1 whole square. And right hand side would become 1 by square root of 2 mod of x minus y, which will be equation of a parabola. Problem 147 says that find the maximum area of the triangle formed by the complex coordinates z, z1 and z2. There should be a comma, which satisfy the relation mod of z minus z1 is equal to mod of z minus z2 and mod of z minus z1 plus z2 by 2 less than equal to r, where r is greater than mod of z1 minus z2. Now we have two equations. The first one is mod of z minus z1 is equal to mod of z minus z2. This represents an isosceles triangle where z is the vertex, while base will be formed by z1 and z2. Now, since the base is formed by z1 and z2, the midpoint would be z1 plus z2 by 2. Now we are also given that mod of z minus z1 plus z2 by 2 less than equal to r. So this represents the interior part of a circle with center z1 plus z2 by 2 and radius r. Okay, so the distance between the segments z1 and z2 will be r. Okay, thus the maximum area of the triangle would be 1 by 2 in Z1 minus Z2 into R. Problem 148 says that if Z1 is equal to A1 I B1 and Z2 is equal to A2 I B2 are complex numbers such that mod of Z1 is equal to mod of Z1 is equal to 1, mod of Z2, this should be Z2 is equal to 2, real of Z1 Z2 is equal to 0, and omega 1 is equal to A1 I A2 by 2 and omega 2 is equal to 2 B1 plus I B2, then prove that mod of omega 1 is equal to 1, mod of omega 2 is equal to 2, and real part of omega 1 omega 2 is equal to 0. So here we are given Z1 is equal to 1, which is A1 square plus B1 square is equal to 1, and similarly we have A2 square plus B2 square is equal to 4. Now we are given that real part of Z1 Z2 is equal to 0. That means A1 A2 minus B1 B2 would be 0, making A1 A2 and B1 B2 equal. Now we are also given that so since this is 4 and this is 1, we can write that A2 square plus B2 square is equal to 4A1 square plus 4B1 square. Now we bring 4A1 square left to left hand side and B2 square to right hand side. We get A2 square minus 4A1 square is equal to 4B1 square minus B2 square. Now since A1 A2 and B1 B2 are equal, we can add 4I A1 A2 to left hand side and 4I B1 B2 to right hand side. So this gives us A2 plus 2I A1 whole square is equal to 2B1 I B2 whole square. Now we take square root and compare the real parts. We get A2 is equal to plus minus 2B1, and similarly we will get 2A1 is equal to B2 plus minus B2. So omega 1 is equal to A1 plus IA2 by 2. Now instead of A2 we substitute 2B1, so it becomes plus minus B1. So modulus would be 1, and similarly omega 2 will become 2. Once we have this, we can say that real part of omega 1 omega 2 would be 0, because A1 B1 is equal to A2 B2. Problem 149 says that let Z be a complex number and A be a real number such that Z square plus AZ plus A square is equal to 0. Then we have to prove that locus of Z is a pair of straight lines, argument of Z is equal to plus minus 2 pi by 3, and mod of Z is equal to mod of A. So given equation is Z square plus AZ plus A square is equal to 0. So roots would be A omega and A omega square, where omega is cube root of unity. So clearly this represents two straight lines. One would be Z is equal to A omega, another would be Z is equal to A omega square. Now modulus of both would be mod of Z is equal to mod of A. Okay, because mod of omega is 1 and mod of omega square is also 1. Now argument of Z would be argument of A plus argument of omega plus, or argument of A plus argument of omega square. And as you know, the value of omega and omega square are minus 1 plus minus square root of 3I by 2. That is, real part is minus 1 by 2 and imaginary part can be plus minus root 3 by 2. So tan inverse would be plus minus root 3. That is, the argument would be either plus 2 by 3 or minus 2 pi by 3. So that's how we have found the argument. Problem 150 says that if x plus 1 by x is equal to 1 and p is equal to x to the power 4000 plus 1 by x to the power 4000 and q is a digit at units placed in 2 to the power 2 to the power n plus 1, where n is in set of natural numbers and greater than 1, then find p plus q. So we are given x plus 1 by x is equal to 1, which gives us x square minus x plus 1, making x is equal to minus omega and minus omega square. Now we are given that p is equal to x to the power 4000 plus 1 by x to the power 4000. So we substitute x is equal to omega. We get omega to the power 4000 and 1 by omega to the power 4000, which is nothing but omega plus 1 by omega, which is equal to minus 1. Because 1 is omega cube, so omega cube by omega will be omega square, and 1 plus omega square is equal to 0, so omega plus omega square is equal to minus 1. Similarly, if you substitute minus omega square, p will again come to be minus 1. Now 2 to the power n is equal to 2 to the power 4k. Okay, because we substitute 2 to the power n is equal to 4k. All right. Sorry, 2 to the power 2 will be 4, so we substitute this as 4k. Or in other words, the other way to explain this would be, since n is greater than 1, okay, So we take one value out, we take 1 2 out, so 2 into 2 to the power 4n. That way you can consider it as 2 to the power 4k. Now this would be equal to 16 to the power k. So if you look at 16, any power would have 6 at the end as last digit. So q would be 6, and then q would be 6 plus 1, that is 7, and p plus q would be minus 1 plus 7 is equal to 6. So with this we come to the end of 15th set of problem. In the next set we will solve 16th set of problem. Excuse me. If you have a comment or suggestion, or you want videos on certain topic, then please let me know in the comment box. If you found this video useful and informative, then please subscribe to the channel, like the video, and share as much as you can so that it can reach other students like you and they can also benefit from this. Thanks a lot for watching. I'll see you in the next video. Enjoy.